Welcome to Eliation, Element Simulation Academy by Apoor Bapat. So let's start with today's session. So the first point is different methods to solve any engineering problem. So the first thing is we can solve any engineering problem. Say you can say a cantilever beam problem using hand calculations. So this is the analytical approach via using some equations and the inputs given for that problem. So this gives us the 100% accurate results because the equations which we have for stress and displacement are 100% accurate. So we get a solution which is very closed and very accurate. Then the next process is numerical method, where we have the mathematical representation of actual problem. We take some approximates and assumptions on the problem with respect to the boundary conditions, geometries, loading conditions, and other parameters. These types of applications are applicable for physical prototypes if not available. You can solve all the real life complicated problem using numerical method. So FEM comes under numerical method. Then the third approach is experimental method, where we see the actual testing condition of the problem. Here we will see again the cantilever beam problem which is actually tested. So the basic problem for this is we have to see or solve these problems with the actual prototype. So we have to set up a testing setup models, everything. So this is very time consuming and needs expensive setup. We need at least 4 to 5 prototypes to finalize the results. Then we'll see some brief introduction about numerical methods. So first thing in numerical method is finite element method. So finite element method is numerical techniques for finding approximate solutions to boundary volume problems for partial differential equation. It is also referred to as finite element analysis. So in finite element method, we solve the problems at a finite level via creating nodes and elements. So my software calculates the values at nodes, and with the help of shape functions, it calculates or interpolates the result for the entire domain. So whatever the values of, say for example, stress and displacement as an output I want, I can find it using FEM at the point level, that where is the maximum value of stress is coming, or where is the point where the maximum deformation is coming using the finite element method. Then the next approach in numerical method is boundary element method, where the boundary element method is a technique for solving a range of engineering or physical problems. It is most often used as an engineering design aid similar to the more common finite element method, but boundary element method has distinction and advantage that only the surface of the domain needs to be meshed. Mainly it is used for NVH, that is noise, vibration and harshness problems. Say if you want to perform a vibration analysis on the door of a car, so you can use boundary element method to perform that, where we don't find the point level deformation or point level stress. We try to find the noise or vibration or harshness or the results for the entire domain, that is the outer surface or outer body of particular object. You can say for example of horn. So what are the vibrations coming at the outer surfaces of horn, that you can calculate using boundary element method. Then finite volume method. So most computational fluid dynamics softwares is based on finite volume method. The unit volume is considered in finite volume method similar to the elements in finite element analysis. Variable properties at nodes include pressure, velocity, area and mass, etc. It is based on Navier-Stokes equation, that is mass, moment, energy, conservation, equilibrium equation. So wherever you do CFD types of problems where you need to find what will happen, the results on the volumes, so you use CFD problems, and the approach which CFD solver takes is finite volume approach. Then we'll see about the finite difference method. So finite difference method shares most common things with finite element method. In general, the finite difference method is described as a way to solve differential equation. It uses Taylor series to convert a differential equation to an algebraic equation. In the conversion process, higher order terms are neglected. It is used in combination with boundary element method or finite volume method to solve thermal or coupled problems. So, say for an example, if any of the problem statement you want to calculate the stresses and deformation at particular location as well as the vibration for the entire domain, so the approach which you follow is finite difference method. Then the next question comes into the mind that why should we carry out the meshing? What is the use or what is the need of doing meshing on any component? So the basic idea of FEA is to make calculation at only limited, that is finite number of points, and then interpolate the results for the entire domain, that is surface or volume. So any continuous object has infinite degrees of freedom, as you can see here on the left hand side of this model, where the number of points, the calculation points are infinite. So it is just not possible to solve the problem in this format. While finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing, that is creating a nodes and elements. So we create some nodes and elements. Actually we discretize this model into some calculation points, and then then the software calculates the values of, say for example, stress, displacement, strain, temperature, whatever output we want on those limited number of points, and with the help of the shapes which is generated via connecting these nodes is called as elements. So with the help of those elements, my software calculates the results for the entire domain. So finite element method only makes calculation at limited number of points and then interpolate the result for the entire domain. Then we will see about the different shapes and characteristics. So in general, 4 shapes are possible, that is point, line, area or volume. A point element is typically defined by one node such as mass element. So you can use a dead mass types of elements, they comes under the point element. Then a line element is typically represented by a line or arc connecting 2 or 3 nodes. Examples are beam, spheres, pipes and axisymmetric shells. So those types of elements which are generated via connecting 2 or 3 nodes comes under 1D types of elements. Then area element has a triangular or quadrilateral shape and may be a 2D solid elements or shell elements. So 2D types of elements are generated via connecting 3 nodes in a plane or 4 nodes on a plane via connecting some area or via generating some area. Then volume element has a tetrahedron or a brick shape and is usually a 3D solid element. So if you connect 4 or more elements on some volume to create some volume of the element, so those types of elements comes under 3D element. We will see some in these types of characteristics in some more detail. Like say for example, my actual model is a rod or a beam structure. So the length of this component is very large as compared to its cross sectional area. So what we can do is we can create 2 nodes at the end of the structure and we join those 2 nodes and create the length of the element. So the finite element expression for these types of problems is defined by using the length of the element that is connecting the 2 nodes. Then, but in actual case, we have to provide a complete volume to solve this problem. So we give input as the area cross-sectional shape in the software. So to calculate the volume or to assume the volume in the software, my software calculates the length, which is the length of the element, and the area which we have given, and it generates the volume and solve the model for the entire domain. So in 1D, we create elements along the length of the component and we give cross-sectional area as the input. So my complete model setup is done. Then in 2D type, say for example, my actual model is shell, plane stress, plane strain, axisymmetry, etc. Or you can say, let's consider some planar component, sheet metal components, or you can say a bonnet, where the length and width is very large as compared to the thickness. So we create the elements along the area, but again we have to generate entire volume to solve this problem. So we give thickness as an input while we do 2D meshing. which after which providing the thickness, my software calculates the complete volume, that is area multiplied by thickness gives me the volume of that entire domain. Now in 3D we have say for example solid components like hub, knuckle. These types of components are 3D components where all the three dimensions are comparable, that is length, width and height are all comparable. So we create 3D shapes of elements which itself complete in volume. So they themselves generate a volume, or the elements are created in all the three dimensions. That's why we don't give any other inputs as additional parameters in the software, because my element itself is have its own volume. Plus we have some different types of elements like spring, mass, rigid links, etc. So that we will discuss later on. Then the next question arises is how we can decide the type of elements. So the best answer to it depends on many parameters, like you can say what is the goal of analysis, what exactly you want as an output. So if you want displacement, stress, strain, fatigue life, CFD, thermal, normal modes. So as you say, different types of analysis have different types of elements. Then what are the shapes of my parts or assembly? Is my model as symmetry? So we can use a symmetric elements. If any one of the dimension is very large, then I can use 1D type of elements. If two dimensions are very large in compared to the third one, then I can use 2D types of elements. If all the three dimensions are comparable, then I can use 3D types of elements. Or should I need to model complete assembly, then I need to use contact elements. So there are some parameters on which my type of element depends. Then also it depends on what type of computational requirements are needed. So do I have to solve this problem using linear or non-linear type of analysis, static or dynamic type of analysis, time domain or frequency domain analysis? Because if we have a complex analysis, then it will take more time to solve. So if it's taking more time to solve, so in the same time I can reduce the type of element to have lesser number of nodes and elements, which might help us to get solution faster. Otherwise it might require a higher hardware configuration also to solve larger problems. So basically the types of elements depends on three main parameters, that is the geometry, that what type of geometry you have, then types of analysis, that is what exactly type of analysis you want to perform, plus how much time you have to solve this problem. So if you have more time, you can get into a complex models, because that will take some more, or complex types of elements, because that will take some more time to solve. If you don't have that much amount of time and want to get the result faster, you can reduce the element configuration to more simpler, say for example 1D or 2D, instead of making them in 3D. Static analysis. So what does static analysis actually means? So static structural analysis determines the displacement, stresses, strains and forces in a structure or a component caused by loads that do not include significant inertia and damping effect. Steady state loading or response conditions are assumed. That is, the loads and the structure's response are assumed to very slow with respect to time. A static structural loads can be performed using ANSYS solver. This type of loading can be applied in a static analysis, include external applied forces and pressure. Steady state inertia forces such as gravity or rotational velocity, imposed non-zero displacement or temperature for thermal strain. Points to remember: a static structural analysis can be either linear or non-linear. All types of non-linearities are allowed: large deformation, plasticity, stress, stiffening, contact gap elements, hyperelasticity and so on. So basically in static analysis we mainly try to find out the values of stress, strain, displacement in static condition, that is the condition where I consider my object in complete static domain and it is not moving. So whatever the force or whatever the pressure or movement or temperature which I am going to apply, or I am considering is they doesn't change with respect to time, they are constant or they are for some particular time. So whenever I don't solve any models which is changing or forces are changing with respect to time, I do static structural analysis. So mainly we see deformation in and stresses in you can say static analysis. So the deformation which we get are depends on what exactly output we want. So we can have the displacement as dependent on the axis. So physical deformation can be calculated on a, and inside a part or an assembly. Fixed supports prevent deformation. Location without a fixed support usually experience deformation relative to the original location. Deformations are calculated relative to the part or assembly world coordinate system, or you can say global coordinate system. Component deformations, directional deformation, or deformed shape, that is the total deformation vector. So there are three component deformation, that is x directional, y directional and z direction, and the deformed shape u are available as individual results. So you can see the deformations in x, y, z direction as well as the global coordinate system deformation, that is the average of these three types of deformations. Then we see von Mises stresses as the output for static structural analysis. So equivalent stresses is related to the principal stresses by the equation this. Equivalent stresses are also called as von Mises stresses, is often used in design work because it allows any arbitrary three-dimensional stress state to be represented as a single positive stress value. So instead of seeing these values individually and combining it all, so we use von Mises stresses which covers the individual directional stresses and combine it with this equation and give us the equivalent von Mises stresses. So equivalent stresses is a part of maximum equivalent stress failure theory used to predict yielding in a ductile material. Similarly, we also calculate von Mises or equivalent strain is computed using the below equation. So these are the two major outputs we see in static structural analysis, that is displacement, which we can see in XYZ direction, as well as stresses, which also we can see in XYZ direction, or we can combine it using the von Mises stress theory. Then one more thing on day 4 which we are going to see is dynamic analysis on the roll cage. So what does exactly dynamic analysis do, or what exactly it means, we'll just see in some brief. That an explicit dynamic analysis is used to determine the dynamic response of a structure due to stress wave propagation, impact or rapid changing time dependent loads. So in dynamic analysis we majorly see the stresses and deformation because of changed because of the force which is changing with respect to time. So we are actually seeing the values of stresses and deformation which are coming and changing with respect to time, which is quite logical. So momentum exchange between the moving body and inertial effects are usually important aspects of the types of analysis being conducted. So we can get a better results, or you can say if we consider front impact, side impact or rear impact of bar roll cage. So those conditions are dynamic because two steady things can't have the impact. So performing dynamic analysis gives a better results. This type of analysis can also be used to model mechanical phenomena that are highly nonlinear. So nonlinearities can also be taken into the consideration, which leads us to have lesser assumptions. So nonlinearities may stem from material nonlinearities, that is the different types of material nonlinear material you can include in explicit dynamic. Then from contact nonlinearity you can use high speed collision or impact through roll cage to roll cage or roll cage to wall. Say for example one component to another component contact also you can define. So if my roll cage is impacting on the engine mounts or transmission systems, so or knuckle or hub or tie rod, how these contacts are happening, you can also predict that in dynamic analysis. And from geometric deformation, for example buckling and collapse. So the prediction of buckling or collapse, or you can say deformation with respect to time can be easily captured in dynamic analysis. Events with time scale of less than 1 second, usually of order 1 milliseconds, are effectively efficiently simulated with this type of analysis. For longer time duration events, consider using a transient analysis system. The time step used in explicit dynamic analysis is constrained to mainly maintain stability and consistency via CFL condition that we will see later on. That what does a CFL condition means? That is, the time increment is proportional to the smallest element dimension in the model and inversely proportional to sound speed in the material used. It means that whatever the time step we give, it depends. So if we give a lesser amount of time step to solve or capture the phenomena, so it will take more time because it depends on the size of the element. So if your element size is very less, and similarly you give very smaller time step, then the solver time increases drastically. So you have to maintain the relation between them. If your time step is very small, then make sure that your element size is comparatively bigger, and if your element size is small, then you should take higher time step, so you should get a results in considerable time of solution time. The time increments are usually on the order of 1 microsecond, and therefore thousands of time step computational cycles are usually required to obtain the solution. An explicit dynamic analysis typically includes many different types of nonlinearities, including large deformation, large strain, plasticity, hyperelasticity, material failure, etc. So you can see these are the different examples of dynamic analysis where the deformation is dependent on time. So you can see here, this for this particular time, this is the deformation which is coming. So we can see the actual phenomena, that how this impact happened, what will happen at the time of impact, after the impact, bounce back effect. All these things can be captured using the dynamic analysis, which you cannot do in static. So static is for a particular instance, but dynamic is for complete duration of the impact happening for your structure. Then one more thing on which we are going to see the analysis on these 5-day training is thermal analysis. So we are going to solve two types of thermal analysis, mainly one where we do the conduction or convection types of analysis, like what will happen to a brake disc when a brake pad is generate friction. Because of that friction, temperature is generated on the disc brake, and that temperature, how it get transferred to a hub or knuckle, and what will happen to a hub and knuckle on that particular temperature, or you can say what will happen to the lock nuts on that particular temperature. So we can perform two types of analysis in thermal. That is, one we consider the conduction convection, and the another one where we see the thermal stresses, that is the temperature, what are the stresses generated or deformation happening on that particular temperature. So one, we see how the temperature is moving from one component to another and how the heat dissipation is taking place. And in the other type of thermal analysis, we will see at particular temperature what is the maximum stress and deformation coming on that particular component. So you can use a steady state thermal analysis to determine temperature, thermal gradient, heat flow rate, and heat flux in an object that are caused by thermal loads that do not vary over time. A steady state thermal analysis calculates the effect of steady thermal load on a system or component. Engineers often perform a steady state analysis before performing a transient analysis. So we are performing a steady state thermal analysis where we are not changing the temperature with respect to time, but in transient thermal analysis, we can give the inputs where we can change the temperature with respect to time. So a steady state analysis also can be the last step of transient thermal analysis, performed after all transient effects have diminished. Points to remember: a steady state thermal analysis may be either linear with constant material properties or non-linear with material properties that depends on temperature. So we can give two types of inputs in steady state, as material having constant properties or a non-linear material with time dependent properties of a material. The thermal properties of most material do vary with temperature, so the analysis usually is non-linear. Including radiation effect or temperature dependent coefficient, convection coefficient also makes the analysis non-linear. So there is another way of making the steady state thermal analysis non-linear is via changing the convection coefficient or radiation effect. Then thermal stress analysis. So the mechanical application enables you to apply temperature for thermal analysis as load. So we apply temperature as loads instead of forces or pressure or moment, and calculates structural analysis for thermal stress evaluation. The load transfer is applicable for case when the thermal and structural analysis shares the mesh, as well as for the cases when the two analyses are solved using different meshes. So we can have the same mesh or same model to perform the thermal stress analysis and steady state thermal analysis, or we can have a different meshes. For cases when the meshes are different, the temperature values are mapped and interpolated between the source and target mesh. So when we have two components and when the temperature is traveling from one component to another component, if the joint mesh, the mesh where the two components are in contact is changing, so my software calculates how these temperatures should travel, how much dissipation is there. So it calculates automatically. But if it is suggested that you should have a common mesh when the two components where it is in contact, so that the transition of the temperature should be smooth and you get a better results of it. So these are some examples of steady state thermal analysis where the temperature is maximum, where I am applying the brake pad frictional forces because of which temperature is generating, and how it is traveling to the core or the hub or knuckle portion of this component. So these are the different types which we will see on day 5. Now one more thing which we are going to cover on the part of analysis is modal analysis on the roll cage structure. So we mostly perform modal analysis to find different mode shapes generated because of the frequencies on the which are generated because of, say, engine frequencies or road frequencies or atmospheric frequencies because of the motion. So we calculate these frequency range, and we see how my component will behave on these frequency ranges. So modal analysis determines the vibration characteristics, that is the natural frequencies and the mode shapes of a structure or a machine component. It can also serve as a starting point for another more detailed dynamic analysis, such as transient dynamic analysis or harmonic analysis or a spectrum analysis. So if you want to perform transient dynamic analysis or harmonic analysis or spectrum analysis, the first thing you have to do is to perform the modal analysis to find the different mode shapes. The natural frequencies and mode shapes are important parameters in the design of structure for dynamic loading conditions. This is because if there is a mode shape because of vibration which is coming, and if the loading is applied on that particular mode shape or deformed shape, then that component is definitely going to fail. So first we have to find out the different mode shapes of that component and see whether the loading is should not come in the same direction where the deformation is taking place. So you can also perform a modal analysis on a pre-stressed structure such as spinning turbine blades. If there is a damping in the structure or machine component, the system becomes a damped modal analysis. For a damped model system, the natural frequencies and mode shapes become complex. So you can perform a complex eigenvalue analysis also. For a rotating structures or machine component, the gyroscopic effect resulting from rotational velocities are introduced into the modal system. These effects change the system's damping. The damping can also be changed when a bearing is present, which is a common support used for rotating structures or a machine component. The evolution of the natural frequencies with the rotating velocity can be studied with the aid of Campbell diagram chart results. So exactly what is happening in modal analysis is there is a physical domain, as you can see here, which is going under the vibration. So with the help of modal analysis, we calculate the first mode, that is out of these shapes, this is the first mode on some frequency, some deformations. Then this is the second mode, third mode, and so on. We divide these entire body in some modes, and we try to see that which mode is giving what type of deformation is, and apart from that, as some external force is coming in the same direction where it is getting the deform because of the vibration. So say for example, if in this particular zone, if my velocity or if my forces are coming in this direction, then it is already buckled because of the vibration, and if some external force coming in this direction, that the buckling will increase drastically. So this component will fail in this particular mode. So that's why we calculate the mode shapes, at least 10 to 15 mode shapes before performing any type of analysis, and decide that which mode shapes is the dominating mode shapes, and my forces should not come into the same direction where the mode shapes or mode deformation is there. One more thing which we are going to see is fatigue analysis, where we see the life of the component, at how much cycle it will work. So this cycle means that for one loading cycle or entire data, that is it withstand, we create some set of the loadings, we consider that set of the loadings as one cycle, and we calculate the number of cycle, that is number of loading sequences, for how much loading sequences my component will withstand. So that helps me to decide that whether I have designed that component as per my requirement or not, because there are sometimes we see that the components are designed in very abrupt way, and they are over designed, and they can work a longer time, and we don't want actually to work those components for longer duration. So we are mainly targeting on such events where my component will work for some duration, and that we require a component to work for certain duration. So we can calculate the fatigue life, and with the help of fatigue life we can reduce the weight or change the material and reduce the life or make the life as per my requirements. So fatigue provides life, damage and factor of safety information, and uses a stress life or strain life approach with several options for handling mean stress and specify loading condition. Common uses for the strain life approach are in notched area, where although the nominal response is elastic, the local response may become plastic. The three components to fatigue analysis are fatigue material properties, which we have to define the fatigue material properties. There are a list of material properties which we have to give the input. So that we are going to see when I'll solve a model using ANSYS. So I'll show you what are the different material properties we have to add to perform the fatigue analysis. Then fatigue analysis and loading options. So to perform the fatigue analysis, we give the cycles or loading data, that which cycle I am considering as single, which loading data we are considering as one cycle, and then my software calculates how many these types of cycle this component is going to work. Then reviewing the fatigue results, so we calculate these parameters and see the results as the life of the component, that is how many number of cycles my component will withstand, and the damage also we calculate. If you find any issues or queries, feel free to contact us via support@eliation.com. Thank you very much.